Welcome to another Keymaster episode, everyone. I'm Sven Ryla, and today I got my good friend Mr. David Hook with me, and we're going to cover the evolution of timestamping. So let's dive right in. So, David, what is timestamping?
So timestamping basically is a method for proving that a particular document was in a particular state at a particular time. It's really quite simple. Basically, you take a hash of the document, a cryptographic hash, you send that to what's called a timestamp server, and then it sends you back a signed version of that hash, testifying that, at that particular time you actually had something which you calculated to this hash. Now, the important thing about this, especially with legal documents and that now from a digital point of view, is that it means that you can then go to someone and say, this document looked like this at this date. And you've got a cryptographic proof, so to speak, of the fact that that's the case.
Nice. And I guess timestamps obviously RFC backed by the IETF because it's been around for a while, industry standard.
Yeah, there's established RFCs for doing timestamping.
Wonderful.
Yeah.
So then how can I trust a classical timestamp in the upcoming post-quantum world?
Okay, well, this is where it actually is starting to get a little bit more complex, because the issue, of course, that we face is that at the moment timestamps have been signed using signature algorithms, which we know are not quantum safe.
Which is RSA and elliptic curve today.
Yeah, exactly.
And then I guess the future is bringing us more towards, would you say MLDSA or SLHDSA? What do you see?
Yeah,
for that
it'll be
post-quantum time?
MLDSA or SLHDSA, depending on what people's preferences are, because there are different security considerations and also implementation considerations with both those algorithms. I mean, the NIST preferred algorithm, though, of course, is MLDSA at the moment, so I'd expect to see most people moving to MLDSA-based timestamps.
Those will be probably really big timestamps.
Yeah, bigger than what we're currently used to. This is true.
And then that kind of leads to, what is an evidence record then in an archive timestamp?
Yeah, so the question, and this is quite weird, because RFC 4998, which is the principal one for evidence records, actually was published in 2010, well before the use of post-quantum algorithms sort of became a real thing. And what they were trying to address in that was, like, what do you do if your signature algorithm becomes invalid, or what do you do if your hash algorithm becomes
Very
invalid?
good things to think
So they were
about.
really, thinking ahead.
Yeah.
I mean, at the time we were trying to get away from SHA-1, so there was a list and precedence of that. But we did kind of think that RSA and elliptic curve were going to be okay, and we just increased key sizes required. There's also an RFC 6283, because there's a couple of minor errors in the original RFC 4998, which are largely due to the fact that they were trying to use ASCII art to diagram the way the algorithm worked, and sometimes that doesn't work very well. But anyway, I digress. So the evidence records have this idea of an archive timestamp, and then there's two procedures that are actually described in the manufacture of these archive timestamps. One which is referred to as hash tree renewal, and the other one which is a timestamp renewal. Now, the simplest case, which is similar to what you've actually got with a traditional timestamp, is you're just basically going, I can reuse the hash. The hash algorithm is still safe, but I need to generate a new signature. So, essentially just generating a counter signature of the original timestamp. And then, you can use your more modern algorithm to prove that the hash was actually that particular value at the time by just hashing the original timestamp.
So now you have like the whole evidence record of this one and now the new one, because we trusted the old hash.
So the structure for that's called an archive timestamp chain. So you can actually, with time, you'd actually build up these lists. So you could always go back and check what the original one looked like. But the most recent element in the archive's timestamp chain is always the version that's regarded as the safest. Now, the other interesting thing is that they address the problem of, like, what do you do if you want to sign a document group, for example?
Oh, yeah, there you go.
Or
What do you do?
want to sign multiple documents with a single timestamp. So the other thing that evidence records introduced was the use of a Merkle tree. And a Merkle tree, of course, is really just a structured Merkle tree, which is just really a collection of hashes with, a single hash at the root. So every hash as you go up the tree is basically a hash of the two branches below it. So the handy thing about that is that basically when you're trying to process a group of documents in that context, all you actually need to get signed is the hash at the top. And then you can break your records up for one for each document just by preserving the branches of the Merkle tree that you need to actually have available to you when you're calculating that root hash. So that actually does simplify, if you're trying to sign or re-sign a large number of documents all at once, you still don't have to beat your timestamp server to death. You can actually, on your side, just, work out what this root hash will be, then get that signed, and then issue a bunch of evidence records showing that the timestamp actually solves that particular algebraic problem of not collecting the hashes.
It's actually pretty brilliant that they thought about this so far
Yeah, no, I think
ago,
they
then
really,
like really forward thinking like that. That was really good.
yeah, and that's the reason why the other step, which is the one where you go, okay, my hash algorithm needs to be replaced. That's why it's referred to as hash tree renewal, because really the context in which the naming's been established is this idea that you probably actually by that point got a Merkle tree that you're actually trying to re-sign. But with a classical timestamp, you can still do the same thing because there's really a Merkle tree of just one level.
Wow. That's
Mm.
evolution.
Yeah, that's what it's about.
All right, guys. So that's our little evolution of timestamping, and we'll catch you in the next episode.